All right, the recorder is turned on, so save all your comments that you don't want recorded for when it's not on anymore. Let me clear up some real estate on my computer. I guess I don't need that, close that. Okay, so 2 out of 4, that's 50% turnout. I'll wait a few more minutes and then start. The agenda for today is to examine the county scale model as threatened last time. And we're only going to examine it in a really cursory fashion, namely because I can't find all my input files for it. But we'll examine it enough to get an understanding that if we ever had to build our own, that we could. And then we're going to get started into a way to do higher dimensional approximation, higher spatial dimension, that is, two-dimensional overland type flows using a technique called interconnected pond routing. And what's interesting about the technique is it's a generic technique, but it also happens to be a brand name of a company in Florida that somehow, I can't say they patented it, but they have claimed it as the name of their company. And nobody's really challenged them on it because there's not that much money in the fast-paced world of civil and environmental engineering modeling that is worth fighting over. Now, if it were Facebook or something that could make real money for nothing, they'd be fighting over it. Okay, so I know Weston can hear me. Anna, can you hear me?
Yes, I can.
All righty. This part of today might actually serve you well for the project presentation that you acquired as a task this morning. So I won't have a lot of details, but it might give you some ideas to proceed with that. So hopefully that has you all excited. I'm gonna, so let me see, how can I get it to, so when I talk to do it, does it take up kind of a bigger part of your screen?
I think so. Like, I can see it, but it's not like.
So is it this big or this big?
It's about half, yeah, half the paper.
Yeah, it is half the paper. I folded it over on purpose. But is this writing height big enough to see?
Yes.
Okay, that's what I'm going to work with. I don't have any scripted or typeset material today, so I'm going to be handwriting. So this video is important for my future because it will give me the ability to generate typeset stuff in later classes. It's important for your future, maybe, in that it's the only note you're going to get from me out of today. So I'll try to go slowly. So the first thing I want to do is look at the county scale model. And by county scale, we're talking a drainage model that could conceivably also include water quality simulation, although it does not. But that's as much as a limitation on the people that put it together so many years ago, where water quality was not a particular concern at the time. And whether it's county scale or not is sort of almost promoting our own self. But that's a large scale model. That's a geographically large scale case. If we were talking artillery shells, the curvature and rotation of the Earth would start to matter to make sure that the shells land on their target instead of on the Walmart that's next to the target. So we're now getting into a fairly large scale. And then really big scale would be basin scale. So that would be the San Jacinto River Basin, the Mississippi River Basin, and actually Mississippi River Basin or Amazon Basin. You're now getting to continental scale. And while I'm sure we could write our own code or convince Swim to do that, we would get laughed at ludicrously if we proposed it. But if the government proposes it and wants to pay us to do it, by all means, polish up your fingertips and start banging on the keyboard. And so on our county scale model, there's a couple things that we need to consider. In no particular order, geometry, of the channels in this case, is going to guide our creation of our simulation tool. I don't know a better word for it, so I'm going to call it connectivity. And that's the link node layout. In and of itself, connectivity has to be correct for the computer model to make any sense. There's no a priori requirement that we do it in a logical fashion, except that we're producing it for fellow people, so it should have some sort of pattern to it. In the case of the example I'm using, Harris County, they have a very peculiar channel naming system, and all the links in the model that I've shown you last time and we'll play with a little bit today don't necessarily follow that channel naming system explicitly, but you don't build a link on one tributary and then move to another tributary and build one and then go back and forth. That's inefficient use of your time as a human being. Ironically, it may be the way you actually acquire real data. And so what you would do in a formal modeling project is you would lay out connectivity the best you can just looking at a map, and you keep a log book as you're adding correct geometry to links, and in the meantime you just have dummies, not the right word, but generic links as placeholders, because it will make it easier to traverse the model when you start to ask questions. The next thing that is generally going to be of some concern is going to be historical inputs. In the case study example of that Harris County model, the input of importance is precipitation. And in principle, whatever the antecedent moisture condition and channel conditions is. And then historical stage. That's cool. So I guess that is staying in focus. This is really weird writing like I'm supposed to write as a normal human being, but having to glance up to something that's this big on my computer screen and see if I haven't screwed it up or not. So these historical inputs in stage are used to choose a green pen. These are used together to calibrate, if you will, our tool. So we would put, assuming we've got the connectivity and geometry already addressed, we would apply historical inputs and use those in the historical stage to calibrate or adjust the tuning parameters. So off the top of your head, what kind of things do we get to tune in a in a surface water model, what comes to mind?
Like, do you mean parameters?
Yeah. What knobs do we turn to make our model agree with observations?
Manning's in
Good.
value.
Good. That was where I was headed. That's not the only one, but good. That's the right idea. So Manning's End is one. The other thing we would control is the whatever the rainfall runoff relationship is. I'm trying to avoid saying unit hydrographs, but whatever converts the rainfall at a drainage area into runoff before we drop it into our drainage network and do the hydraulics are the main things we have to control with tuning. And I'm just going to put the word storage here because we have some aspects of that are involved on how we represent the actual land surface to our computer program. Because while we could create a computer program that's just fine with buildings and individual trees in it, eventually that has to be averaged into some sort of on subcatchment storage before it gets into our drainage network and we start doing hydraulics. So I've just explicitly taken a step down the rabbit hole where we're now starting to integrate our hydrologic and our hydraulic concepts. So let's suppose we go through that and we get it to the point where we're comfortable that for our historic inputs, we get a reasonable representation of historic change. Now our model has some utility to it, and we would give it a challenge event. I'm using fancy words on purpose. Essentially, we do the what if that we're actually really asking. In the case of that particular example, it's rainfall. And we're trying to predict the response, which in the case of Harris County is generally the stage or how deep the water is, whether there's portions of the area that become inundated, which is the big fancy uppity word for there's water making my socks wet as I walk down the street. And nobody likes wet socks. I don't. Especially if you have cats in the house, you wonder if that's water or not. So, okay, let me bear with me while I pull up some sources of where one might access these various pieces of data. And let's see, I've got to share my screen. So now the writing just gets, oh, actually it doesn't lose size too bad. In a way, that's kind of cool. It sort of keeps a set of notes up there. And so using, again, Harris County as our example, I typed in HCOEM into my Google search bot and eventually got to this map. So I will confess in terms of full disclosure, I haven't actually dealt with Harris County in years. So it used to be, first thing is the map never used to do this. So that just baffles the crap out of me. And it used to be through the HCOEM. So this flood warning system is kind of new, but the map is reminiscent of what I'm used to. Let's just pick a place. So this is showing, and before I go into this one specifically, because I'm very familiar with the Harris County Alert Network, a lot of major metropolitan areas have a network something like this. So this one I'm choosing as an example because it's the only one I have a county scale prototype model of, and it's one I'm personally quite familiar with. But there's something similar for Dallas. I think in time there'll be something similar for the Lubbock area, but given our whole role on the planet Earth, Lubbock is just kind of like a swirly backwater as far as the rest of the country is concerned. That's not a critique. I'm kind of comfortable with that. That's a good thing. But other major metropolitan areas, Dallas, Fort Worth, San Antonio has a network not nearly as dense as this one. The Harris County one is quite a bit dense, and it's not like there's no gauges down here in this part, but that's not part of Harris County, so they don't care. Each of these boxes represents roughly, if I were to count, in 2007 there were 106 boxes on this map. It doesn't look like there's that many on it right now, but there's parts where it's really dense. And I'm just going to pick this one, and that's completely arbitrary. So this is site 2115, Langham Creek at Clay Road. So it's telling us where the location is. And in the olden days, you would double click on the box and you get access to the data files. Now they've made it a little bit trickier. You click on more information, and it has two tabs, stream elevation and rainfall. And I know I'm showing you a website and you're going, so what? I mean, I could have figured that out years ago. I didn't need some idiot professor to teach me that. I agree with you. But I'm trying to illustrate the kind of data one would have to work with if you wanted to make one of these county scale models. So this has a rainfall record. In this case, see the 14th and 15th, so Sunday up to today, so not very interesting over that particular time period. And it has a stream elevation record. And so in this case, the blue line is the time series of what the stage is at the measuring station. Think of it from our swim model context. It's the same as the time series blue line of what we had as nodal depth in swim. Same kind of conveying the same kind of knowledge. In this case, they have a red line, interesting color choice, that they call flooding lightly. Back in the olden days, that used to be called flood stage, but government agencies are afraid to commit to anything. So they're calling it flooding likely. Oh, good. Welcome, Richard. They have the timestamp of the sensor ID, and then the computed or the reported elevation. And the sensor, all the sensor is it's these are probably bubbler gauges. So all it's actually sensing is a pressure, and it does a little bit of arithmetic in the data logger to convert that to an elevation. And if there was anything interesting going on, there'd be portions of time where the sensor's all messed up and giving completely goofball readings. And you can tell looking at it. And us, the engineering modeler, would have to interpret those goofball readings. Here they have some historically significant events. So they have Tropical Storm Francis. I'm surprised they don't have Tropical Storm Allison. I guess it didn't do much damage at Langham Creek and Clay Road. And then they had when Eisenhower came through, Hurricane Ike, and then Hurricane Harvey, and they have the recorded maximum elevations at their gauging station. Okay, so technically that's historical data, and I believe in principle you could go and try to extract the historical data one gauge at a time. In practice, that would be an active dumbness, let's go back to the main thing. And in the document library, there's a category called Data Archives, and it has records from 1986 up to 2011, and it baffles me what has happened between 2011 and 2021. So if I were to follow up on this, or if you ever have to do this, let me know. I have a former PhD student who works at this organization. Here's the list of gauge locations, and there's a monthly rainfall from 87 to 2021, and that looks inclusive. So what's going on in these missing years, I don't know. I personally have data from the I think earlier than 1986 up to 2007. Oh, so big deal. There's more data. They take a long time to get these other data published. And I think it's because they're trying to do real-time data. We will publish no records that have not withstood the test of real time. But I was unaware that they were almost 9 years behind. They always ran a couple years behind. So something peculiar has happened. So I'm just going to click on one of these, probably going to regret that. Sure, that's why I did that. And I'm just going to go take a look at, oh, they're not that big. Oh, they must have found a way to make the data files incredibly huge. Classic. The data files used to be quite compact, so they probably have pictures in them now. Maybe I won't download it. Click on that. Go down here. Huh. My computer is extremely angry at me now. All right, well, let's stipulate that we could download. I wanted to show you what one of them looked like so that I could give you some guidance, because all the ones in the world have a similar, completely undecipherable structure. Let's see what happens if I reload the library. Data archives. We'll pick 2011. Click zip and download, and they should have the audio cards sing to me like zippity doo da zippity. And okay, wait, I can't. Oh, you bad words. Safari can't show it in the Finder because the file has moved since I've downloaded it. But the file cannot be moved. Classic. They got me again. Oh, how I hate thee. That's a real good stunt. It's good to see they're up to their old antics. So around 2003, 2004, Stu and I did quite a bit of work to automate this flood alert system. And at the time, accessing data, they had all sorts of interesting antics where you couldn't get it. And it's good to see that they're still up to it. And I'm not going to log in and register in the source of getting data. But I will try one more time. Nope, it's not going to let me get into it. Refresh. Let's pick an old one. Zip and download. Issue the command. I need to know where it's sending it. So we go here, we search for 1986. That's okay, that's what I'm after. And here's what the contents look like. So the first 4 digits of the file name corresponds to a location. So that's site number 159. We could go back to this map and attempt to find site number 159. And I think that's over here somewhere. 240. They're not exactly in logical order. So 159 corresponds to the 100 series of ditches, and so I have to poke around and find them. Well, 160 is close to 159. It's somewhere down in the southern part of the county. And let's see if the stream elevation is 160, rainfall is 160. So this is why you want to get paid to do this kind of work. 40. So 159 is going to be down in here somewhere. And it actually may be a discontinued gauge. There's 150, 105. Okay, well, that's beside the point. We could find it if we were diligent enough. And it has a date, a time of day, and a number. And so I'm thinking site 159 without knowing what it is. Based on those numbers are far too big to be a cumulative rainfall. So that is a gauge height, 19.64 feet on January 9th, 1986 at 2 in the afternoon. And if you look at these gauge heights, I retract that statement. This actually might be accumulated rainfall. Now these are gauge heights because they're going up and down. So if you have the hash table that associates the station ID with whether it's a stage or a rainfall, you can tell from that. It looks like on September 16th of that year, stuff got pretty interesting because we're up in the 40s and so on. So there's one of these for each year for each station. Let's see if we can find site 160. That's also gauge. I'm trying to find a rainfall one. Because what I want to point to, if I can find a rainfall one, I want to point something out that's pretty important. Okay, here, this is rainfall. So they, in the 80s, in the 90s, and probably not to present, but for about a good 30 years, we actually recorded zeros. Because that's the way data loggers worked. And then people who built data loggers got smarter and only had them record data if something was happening, which is much more efficient use of your telemetry bandwidth. NASA figured it out 50 years before hydrologists did. Is you only send data when something interesting is happening. But that's the way it is. And so these are accumulated rainfall. And let's see what we get if we get up. So this one has a reset in it, 0.9. See if we can get up to 99. So accumulated up to 13, and then they did a reset. And so if we were to plot this, these look like kind of wiggly triangles going up to a peak and then they drop, and wiggly and going up to a peak and then they drop. And this data as presented is not usable in any imaginable computer model. You would have to write your own scripts, which you know how to do because you had to do it once. And you would have to read through the data and either convert it into uniformly spaced in time increments, or what I did is I just integrated everything, made it a completely cumulative thing, and then differenced the cumulative one, because that was the easiest way at the time to catch these resets. Otherwise, the analyst, teaching a computer what to do when it reads a 14 and the next line a 0 is phenomenally difficult. They're not the brightest things in the world. But teaching computer to add a 0 to 14, it's totally happy to do that for you. And then you can add this to that 14, and you can essentially accumulate all these numbers. And these files are only 1 year long. At the end of that year, you can either difference that file to get incrementals or just use it in cumulative space. And so if you're working in another area other than Harris County, I mean, it may seem obvious, but you need to examine as the analyst the raw files that you're working with to see if you can see if there's these hidden resets buried away in the file. So here's another reset that occurs right there. Normally, I thought the gauges, normally they could record up to 99 units, but that one's resetting as it hits 10. The other reset was at 13. So there's no physical limitation per se. It's got to be in the software. That one reset at 14. And there's another reset up here somewhere. I guess not. There's a reset at 10. So the 10 to my memory seems familiar. It seems like they were designed to automatically reset themselves around 10. And so what I mean by a reset is when it hits whatever its reset value is, it basically dumps its data and then starts everything over at 0 again, or in this case, 0.03. So that must have been a busy day on August 6th of 1986. So those are what the data files. Oh, that's why the files are so big. They've got pictures. Everyone loves pictures. Actually, that'll let us find out where that gauge is. A rain gauge at Glenlock, a rain gauge at Timberlock. And in the 80s, we used to do stuff by drawing with our hands because Excel 94 hadn't been created yet. And here's another hydrograph. So the data is actually contains an awful lot of stuff, and I think I regret downloading some of that. Okay. So to build a major model, we would download all those data files. We would write our own script to process them into a usable fashion to go into our computer model. Let's again go back to one of these sites. We'll take NRG Park, which I think I know is the Astrodome. There's no information at the Astrodome.
Wait, I thought the Astrodome was a different building.
It is a different building, but it's all the same parking lot right next to the
true.
Holiday Inn, where if you used to go to a ball game, for $6, you could get a beer with your parking spot. Those were the days. So the other
beer is like $12 at a game. So
I remember taking my nephew once, and I don't think I drove him. I think my wife picked him up, and I was sitting there at the bar at the Holiday Inn waiting for them because we parked at the Holiday Inn because we talked to the barkeep, and if we bought a beer, they said fine. We missed the shuttle bus to drive over to the ball game. It's not that far of a walk, quarter, half a mile tops. So we finished the beer, and my nephew was all anxious. It's like, come on, we'll miss the game. It's like, I don't worry about it. Nothing happens in the first inning. And we're a quarter mile away from the park, and you could hear the crack of the bat that just sent one out of the park. It was a home run. He was so pissed at me. To this day, he's pissed at me. He's got 3 kids of his own, so I still remember that. So don't ever say that to young people in your family, that nothing ever happens at the beginning of the game, because God is going to strike you down right there and then and make an absolute fool out of you, and you'll never be able to recover from it. As punishments from God goes, that was pretty mild. Wasn't like there were lightning bolts and stuff. But anyway, that's beside the point. The other piece of information we obtain is the base elevation for the sensor. And they're showing us a hypothetical cross section. Now, most of the channels in this particular community are engineered channels, and they are reasonably well approximated by a trapezoid. Usually at the top part of the trapezoid, they transition from concrete to dirt with crappy grass in it, a few shopping carts, and bags of half-used methamphetamine, needles, etc. I'm kidding there. But a trapezoidal channel is as good a guess as any. And I'm trying to remember what I'm pretty sure the bottom width was on the order of 50 feet. There's usually a 10 to 12 foot pilot channel, a little rectangular channel down here. And these are designed so that you can drive a fairly large vehicle on either side of that pilot channel. If you're stupid, you can actually drive your vehicle into the pilot channel, but that's a one-directional act of stupidity. And they're made to drive down into so that they can access them for cleaning and maintenance. It's not for regular people to drive down into. You're supposed to be a contractor or have a flood control vehicle. On a completely different project, unrelated to this, but this might be helpful field technique for you. If you're working on a landfill in Northern California, don't take the company four-wheel drive vehicle around the side of a hill to save time. So you don't have to drive up to the top of the hill and go to the next monitoring site, because it turns out that that vehicle will roll over onto its top, roll over again onto its feet, and yeah, you save time. You got to the bottom of the ditch that you had intended to get to, but it leaves evidence on the vehicle. There's chunks of dirt, and there's a broken roof, and a huge bruise on your shoulder from the seat belts. And so if you have to go down steep grades, you want to go straight down them or straight up them. Don't try to go sideways up them, because cars are not, they're not called, there's never a vehicle that's been named an Eileen for a reason. Okay, so that's how you access data for a model such as this. So next thing, let's go take a look at what came out of all that. I think I have to go Amazon Web Services. And I was logged on earlier today, but naturally I moved my mouse, so I guess I have to do it again. Someday, once you have a growl, I guess that's a 3. 3. Actually, I want to try an experiment. I hope you all don't mind. So I've read that these don't actually really care much what the data input is, as long as we act like a human being that's struggling to read it. Oh, it's smarter than I thought. Pandate, P-A-N-D, P-A-D-N-N-A. So what I read was bullshit. Okay. So the point was on those CAPTCHA things, you don't have to get every single character correct, but you've got to kind of stagger the input so it looks like a human did it instead of some machine that's just pulling numbers out of the internet. And we will connect with it, and we'll just take a look at our model that we have already built. I'll warn you now that the data that I left behind for all of us to use is neither calibrated nor is the geometry quite correct yet. But since I have the Harris County map, unless I just destroyed it. Oh, good, there it is. I hate it. I missed the old one. The old map was static sizing, so everything stayed the same size. But they have highly paid programmers that have nothing better to do with their lives than to keep making that stuff all cool. So now when I bring up the model, I think it'll make a little more sense than last time. Oh, I'm actually embarrassed. Did I show a model last time? I thought I did. It's not Confluence Houston. It's not that one. I must not have uploaded it yet. Well, that's kind of stupid. Oh, well, today may get shorter real quick. I don't want any Bing suggestions. I want to log in. Oh, that was my mistake. I am so sorry, Microsoft. I didn't mean to use one of your products. Yay. I didn't even know I had a Reddit account. Huh. So this should be around 15 or 16. Okay, yeah. I know I never downloaded the file, did I? So let's see if we can find an input file. There's one right there. Right click. Right click again. Reminds me of a TV show I used to enjoy called, I think it's called Come Fly With Me. Press fries again. It's a hilarious show. I'll try to get the name of the show. It's got to be on Netflix or Amazon Prime somewhere. It was British comedy. They're able to play knuckleheads really good. Okay, there's an input file, and I think I'm going to want, let's see, it does BMPs. Do I have anything that remotely resembles the BMP? Not sure it can load in a PNG, but let's give her a try. Sure, that's what I'm expecting. Okay, we'll see if it can load in this image file. It may not be able to. But let's go pull up our file called Design 1 Harris County, open, and so this part's an experiment. I don't know if it, here goes nothing. Oh, I am seriously impressed. That's 11-year-old file and so forth. So I will leave that up for a moment, so you can visualize in some aspects how this was put together. So each of these small rectangles represents a subcatchment or a drainage area, and it receives rainfall from somewhere. In this case, I think there's only 4 gauges in this prototype model. In the actual Harris County model, there's 106 rain gauges that are used for active modeling. So this is clearly a prototype, and the area of this particular subcatchment is 3,600 acres. So that's 6 square miles about. So that blinking box right there represents a fairly substantial drainage area. That's where the hydrology occurs. That's where the rainfall is converted to runoff, and then that runoff is dropped into our junction 1179, which just has a name, but those are not willy-nilly names. They correspond to locations on this map. So 1179, let's see if we can find it. It's on Cypress Creek, which is up here somewhere. Little Cypress Creek, 1210, 1150. They have changed their numbering scheme in the last 20 years. Go figure. That's Cypress Creek at 290. Maybe if I zoom in, they must have shut down some gauges. So I have gauges in the model that no longer exist. So there's 1170, 1175, and I think 1179 is up in here somewhere, or was up in here. We'll use 1175 for the dog and pony. So it's Cypress Creek at US 290. And in this case, we have 1179, which does not have a naming convention associated with it. It's probably close to there. We'll go to 1189, which would correspond to 1175. There's more gauges in the older data. That is very crazy. 1180. So 1179 is somewhere between these two. And the numbers are just 1189 should be somewhere up in here. This particular map does not reflect the total number of gauges that they have that are active. So I'm a little confused as to why they are hiding data from the public. At some point, at some scale, I guess you have to, because even if you zoom in, we're not getting those intermediate gauges, or perhaps they've consolidated them together. I'm going to give them benefit of the doubt, and they weren't being sneaky evil government. They probably had a good reason. So that's what those black boxes are. We'll just pick this other subcatchment. So in this particular thing, it looks like all the black boxes are intentionally corresponding to 6 square miles. So maybe my numbers are the ones that are wrong. Maybe mine are the composited ones. All right, so in this area right here, you'll see that this has a name called conduit temporary, and that would be, again, how we would create stuff. So at the time of the building of this prototype, there was insufficient information for these conduits, so temporary ones were put in place, and we'll just go look at the what a temporary conduit is conceptualized as. And so here's what was used for a temporary conduit. So it has a V-notch part, really steep vertical walls, and then a fairly substantial overbank. This was drawn this way so it would be obvious to a future user that that in no way, shape, or form represents something that's real yet. So you could look at that and go, we can't build stuff with vertical walls 30 feet tall. So this is clearly the original builder's way of telling us, I don't have enough information here, but I do have a need to maintain hydrologic and hydraulic connectivity. And what's interesting to me is that these temporary conduits actually join into Buffalo Bayou rather than picking up Bray's Bayou, which is what I think they're supposed to. So we'll leave that for the time being. Let me suppress the background map. So I'm going to put that away. And there is our integrated hydrologic and hydraulic model. Let's zoom in on some portion. And this gives you an idea of the complexity of what's really just a prototype. And if we go look at our outfall boundary condition, it's a free outfall. And let's look at our rainfall. So again, in the real system, there's well over 100 to 200 rain gauges, somewhere in that ballpark. And here in this one, we're representing it with 8. So this rain gauge is kind of integrating that area. This rain gauge is that area. And in a prototype, you have to start somewhere. And it's my conjecture that it's easier to start with a few fake ones and then start adding real capability one step at a time. For a couple reasons. It helps you maintain control of what you're doing. It greatly increases the number of billable hours, which your boss will like. And you don't get lost doing what you're doing. So here is a clearly an artificial input rainfall. So nothing very interesting happens until hour 30. And then we get, see if these are intensities or cumulatives. Those look like these are intensities. Then we get an inch an hour for 3 hours, it looks like. Yeah, to 3 hours of an inch an hour. Let's look at this other rain gauge. And I'm pretty sure it's going to have the same time series. Okay, so this is clearly the prototype model. All right, so why would you build a prototype model? Well, the obvious reasons: to get the connectivity. I've already stated that I think this channel is supposed to connect to that point. Let's run the simulation and see what happens. Okay, not bad. And let's go to, see if I can find Buffalo Bayou. That's roughly just to the east of our confluence model from last time. And if we look at the flow, indeed our little 3-hour storm generates pretty damn substantial discharge. And that's because every contributing area upstream of that point is getting the same inch an hour for 3 hours. Let's go to the actual junction, which is our confluence, and see what the flow depth is. If you recall, in our confluence model, we had numbers like in the 20s, I think, for depths. And sure enough, we get numbers in the 20s for depths. And then what would the next step be? Because I've been doing all the talking, you all have been doing all the paying attention. That's cool. But let's say that we decide, okay, our prototype model is functional. We don't have goofy response at all. 1 inch an hour for 3 hours is a pretty decent rainfall in the Houston area, especially if that was uniformly distributed over the 600 square miles that's represented in this picture. That would produce substantial amount of flow. Then our next thing is to take each of those gauges that we've downloaded and convert that data into a rain gauge time series for the particular subcatchment that's contributing to a node. And then the stage time series is applied at these junctions. And then we'll adjust our Manning's N and the hydrologic part of the model until they agree. That would be the calibration step. And then at that point, we now have a tool that we can ask design or operation questions of. So that is our county scale model. The difference between this and where we started 5 or 6 weeks ago is really just the number of interconnections. This is all still largely one-dimensional flow along any of the possible pathways. And actually, let's go see what Buffalo Bayou does. So that's supposed to be the upstream end of Buffalo Bayou. I'm personally curious. And we'll take it all the way out to, okay, so now we're going to challenge the software because it has to navigate the directed graph. Oh, it did it. I'm impressed. So there is our profile going from the upstream would be Addicks Barker Reservoir somewhere here, all the way down to the last part is representing Galveston Bay. And there's not a drop of water in it anywhere. That's pretty impressive. What did I do wrong? Oh. Huh. Oh, that's right. Nothing happens until, there we go. I was scared I had, so now we'll see our little flood wave, if you will, pass through the system. Okay, so that's a prototype model. And then from here, the next logical step would be to start populating the correct geometries for the links, the correct roughness coefficients, Manning's N's, if you will, for the links, and the best hydrologic response we could do for each of the subcatchments, and then possibly provide a correct tidal boundary condition so that the tidal behavior of Galveston Bay is very well documented. So we don't have to do a free willy outfall. We could do a proper tidal outfall. We would have a challenge of putting the rain gauges and then correctly connecting them to the right subcatchment. So the message is, once it gets to this level of complexity, there's nothing intellectually hard about any single piece, but once you get a bunch of pieces together, there's a whole lot of organizational skills that you'll have to practice to go from this step to something that would be a usable tool. And I apologize for not having a usable tool to show you. I assure you one exists, but I couldn't find it on my computers. I didn't look all that hard. But there are a sequence of steps after this, and then you would have a usable tool. Now, what this doesn't do is, let's just pick this subcatchment and load in the backdrop. I didn't mean to take this long today, so sorry about that. I wanted to get to the interconnected pond routing. I think I can get it started. We're representing 6 square miles in this area by that blinking black dot. So it's pretty implausible that a single 6 square mile watershed in that area magically collects everything around it and takes it to that node. So our next level of complexity that we might want to examine is, I'm going to fix something because it's going to drive me batty otherwise. It's not letting me do it. I want to make it follow the creek it's supposed to follow. But anyway, I'll be done with that. Okay. So our next level of complexity would let's pretend that this imagery is somewhat reflective of the actual topography. So we have flow that's trying to come that way along here. This looks like a ridge line, although that looks like actually probably a highway. And so flows south of that highway come down into this drainage network, and north of the highway make it over to here. And so we might be concerned, legitimately so, with, we can't represent the 6 square miles here as something that just drains to that point. We have to be concerned with how it marches overland to get to that point. And that would move us from the world of one-dimensional link node modeling into a two-dimensional overland flow. Doing that and being faithful to the actual fluid mechanics is not easy. However, we can do a cop-out, which is often adequate for civil engineering projects. The cop-out we'll use is something called interconnected pond routing. So actually, that was a pretty good segue, if I do say so myself. So let me shut down this swim model unless anyone has questions about it. It's just a swim model like the ones you've built before. It's just got a lot more pieces to it. There's nothing in this particular model you've not seen in other models in this class. And I'm looking at this right here. So Weston, you're familiar with the Houston area. Do you know what this structure is that my cursor is cursing on?
Yeah, isn't that George Bush Park?
It's, yeah, this dam, I think, is the Addicts Reservoir.
Yeah.
There's they did a really brilliant thing from a civil engineering perspective, built major subdivisions in the storage pool of a reservoir.
Yep.
George Bush Park, you're right. I think it's along one of these roads.
Mhm.
You're in the right area. So anyway, this part of this particular model, I now understand why the students that built it for me did it this way, because they were taking stuff out of this storage pool and following the local hydrology, but it has to pass through the dam control structure. And I know there's another control structure here, but it is not routinely activated. So there's nothing wrong with actually the swim model. It turns out whoever did the base map, that'd be me. This yellow line should connect up there. So that's the base map drawer's mistake. And that happens. Okay, so now I'm going to exit this swim model and we will do hand drawing for the next 10 or 15 minutes until you all pass out from fatigue. I'm just kidding. I hope you don't pass out from fatigue. Okay, close that. Everything is closed. I'm getting better at the cloud computing thing of closing things down. And I know Anna's using cloud computing. You'll probably want to do this too so you can reconnect later and not have things get all screwy on you. So I just shut everything down and then I disconnected. Okay, nobody cares about the fastest way to clone an SD card. So let me turn off my screen sharing and go back to my homebrew overhead protection projector. Okay, line it up. Get my pencils. So let me draw a sketch of a watershed. And all watersheds look like that. I'm trying to draw two identical ones. Okay, that's not bad. If they look like chili peppers, it's because I'm hungry. And here's our watershed on the left, and we'll have a couple of tributaries. And here's what's supposed to be the same watershed. Up to this point, we've treated our modeling either in this class or other classes, or that model that we just presented, is perhaps we're taking this entire area right here, collecting whatever runoff it produces, and applying it to some point in our drainage network, maybe right there. And the drawing I'm doing is conceptual, so the actual accuracy isn't terribly important for the drawing. And then maybe we take another subwatershed like that, bring our flow to our drainage network, another one right here. I'm just going to run it right to the network. So each of these shaded areas I'm drawing represents one of those blinking black squares in the swim model. I have to look up at the video, be sure that everything's still in the right place. And you've all done this in in Dr. Herman's class. If you had hydrology from him, and since he's the only one that teaches it, you probably did. And we'll get our last two down here. Okay, something like that, where the red arrows represent the collection of the various little subwatershed outlets. And so there's no, that's not new. You've seen some variant of this before. Well, but that is inherently a one-dimensional approach. complex one-dimensional, but one-dimensional nonetheless, because it somehow magically presumes that a parcel of water right there, one there, and one there, somehow all manage to get to this point right here, or wherever we've drawn the connection. An alternate way to look at the same watershed, let me actually label this. This is classic link node. Lumped subcatchment. So we would have properties of these subcatchments that would be important, would be their area, contributing drainage area, some measure of slope, and some measure of travel time or time of concentration to get this sub area into the portion of the problem where we care about the hydraulics. And you've done that in some way, shape, or form. An alternative way to examine the problem would be to superimpose a grid, and I'm taking a lot of liberties with a ICPR concept. And the grid, I guess, could be very fine, but I don't think we gain much for that. And now this grid cell behaves just like a blinking black rectangle. But if this cell is at greater elevation than that cell, there can be flow that way. If this cell is at greater elevation than the one to the right, it can flow that way. And we can keep track of those different overland flow paths. And I'm drawing these kind of funny on purpose. And that all of a sudden gives us an ability to get some feel for the topographically driven overland flow. And I'm actually restricted in my drawing capability because I didn't make my grid fine enough. And this is still link node, but now the links aren't necessarily in the channel, and this is called interconnected pond routing. And let me go ahead and, yeah, got 4 minutes. I will attempt to sketch how the name interconnected pond routing came about, and then we'll pick up next time with some more details on this. Okay, so there is a half a sheet of paper, but put the top like that. Don't throw these away, you might need them. It's me talking to myself. So you always know it's a good lesson when the instructor's talking to himself. So remember those cells that we've just identified. Let's just sketch one of them up. So we superimposed an artificial grid onto our study area. And so that grid has some bottom area, 6 square miles or more like 30 acres or something. And we can consider that there's also a cell adjacent to it. Starting to look scarily familiar? Supposed to. So there's another cell, has a similar surface area. We can take rainfall, which is green, and comes into each of those cells. And if there is no way for water to get out of that cell, so that green arrow can come in, if water can't get out of the cell, what does it have to do? Anybody? The cell's a bathtub. The water's coming in the bathtub at standard bathtub entry fee. What does the water elevation do in the bathtub?
It goes up.
Excellent. You are correct. So if the water can't get out, the water level has to go up. And in interconnected pond routing, we provide a connection. So if the water level in this left cell is up here, and the water level in the right cell is up here, and this will be the end of tonight. This is for all the money on Rigel 12. Which way will the water flow in our world?
To the right.
Oh, very good. You get all the money on Rigel 12. So go when the class is over, fire up the TV and watch old Star Trek reruns, because I do that some nights when I'm having trouble sleeping. Worf is still a funny looking character, even years later. So the way I've drawn it here, I drew that as a conduit. I drew it as a pipe, but it doesn't have to be a pipe. The conduit could be a channel that looks like that. It could be a channel that looks like that. It could be a channel that looks like that. Oh, it looks like I'm spelling a word, or something like that. So that's our link. And now our areas become our nodes. And there's no requirement that they have to line up like this. We could also consider this cell here. And that has a link, and that's how we can approximate what we would call two-dimensional overland flow. Now, the original interconnected pond routing has the ponds as relatively big things and does indeed route them with pipes. But there's no requirement that those pipes can't be some sort of channel cross section, nor is there a requirement that the distances between the two ponds have to be particularly large, nor is there a requirement that it cannot do adjacent cells in multiple directions. And how many of you had groundwater modeling from Dr. Rainwater? I got two of you, and I imagine Richard raised his hand. There's not much conceptual difference between interconnected pond routing on a watershed and if that were an aquifer system where you would break everything up, because in an aquifer model, at the centroid of each cell, what properties did you provide it? If you remember, you provide it with a storativity or a storage coefficient, which handled the case when the water came in but had no way to come out. It would increase in storage. And then between adjacent cells, there was a harmonic mean representation of the hydraulic conductivity between the two cells. And that plays the same role as the conduits do in a surface water system. So although SWIM was never set up to do this, it is a tool that we can fake to do this with. And you fabricate your initial or your prototype models in some sense as if it were a groundwater model where the cells represented finite areas and the connections between the cells handled our hydraulic, in this case, conductance. And I went 2 minutes over, and I'll stop now. We'll pick this up next time. And the last 10 minutes, did that kind of make some sense? Okay, I'll revisit the sketching again next time, because that's the important step in tricking SWIM to do quasi two-dimensional flow, is you mentally have to be able to make the step to superimpose a grid on your system and then build your hydraulic model as if it's going from grid cell to grid cell. And keeping in mind where you have known drainage network, you can superimpose that on your already existing grid. And so we'll pick that up next time. Have a good evening. Go get some dinner. And thank you all for your patience and attendance. And I hope you found this stuff kind of cool, because now we're getting into pretty exciting stuff. There's one person I met once at CDM. Yeah, I think that's who it was, CDM. Camp Tresser and McKee, or as I teased him over beers, can't do much. He's the only other person I ever met that realized that you could do this with swim and didn't have to pay fairly large licensing fees for unnecessarily complicated 2D modeling. And he modeled the Bergstrom Airport in swim, and they were amazed that it could be done in that. And he reminded them, that is why we charge you $400 an hour. So with some creativity, you can use tools that are readily available to answer questions you want. What we can't do with ICPR is, if we're really worried about the curl of the velocity vector, it's incapable of resolving that information. It's the wrong tool for that. And near the end of the semester, we'll look at some tools that can address that, mostly in demonstration methods. So with that, I am going to say goodnight to everybody, and I will see you on Wednesday night, and we will pick up and continue with this. I haven't looked to see if everybody uploaded their project ones yet or not. If you did not, let me know by email, and we can talk about opening up the uploader again. If you did, I guess I have to get off my butt and read them and make comments. So again, have a great evening. Bye-bye.
Bye.
Bye-bye.